So obviously too many poly there. Let's show golfer instead. All right, so welcome back. You know what, for most of you, I think you survived exam number 1 well. I hope it's not too traumatic. Oh yeah, hi, afternoon, Wei Xiang and Angel. Okay, welcome back. And let's go on and go over the to-dos, the announcements. So we have the lecture link and the usual Google Meet session link here on the announcement for week 7, episode 12, which is today. And very gentle reminder, PA number 4, as well as 5 quizzes are due this week. Okay. And hey, there's a good reason for this because next week is spring break. So we don't have lectures next Tuesday. So you're given a little bit more quizzes to work on for Saturday. Well, as I listed here that we have 5 quizzes due, chances high that in case we get delayed a little bit longer than usual, then it will be quiz 16 to 19 only. Okay. So we'll see. By the end of tomorrow's lecture, we'll see whether we need to adjust that. And the topics today. We are not quite yet done with chapter 2. We are almost done with chapter 2. Okay, so just the last bit. Okay, so last Tuesday at least, we were talking about transmitting video. So video are visual signals that we turn them first to digital form into bits, and then we think about how we compress them such that we only need to send very few bits, and yet at the receiving end we could restore the original video in good quality. Okay. And there you see also that before we send the videos, what we do is we break video, usually very long file. We cut them into chunks. Okay, and each chunk we actually compress the videos into different resolutions. As a result, the streams, okay, for different resolutions can be thinner or thicker. And how we determine whether we download a higher resolution video stream or lower resolution video stream, if you recall in Dash, The client side would do the measurement of available bandwidth. And depending on how much we have, we'll download the stream that is just below the available bandwidth so we don't overwhelm the network. Okay. But we haven't talked all that much about where we download these video streams, where these video streams are stored. Okay. In the introduction of chapter 2.6, you heard me saying that, hey, the video demand is much bigger than like 2 decades ago. So having only one server is not going to work. So we do have this CDN thing. We have a network of video servers to allow us to download video, and to allow us to download video in a way that the server is as close to us as possible. Okay. So the last bit today is let's talk about CDN more formally. And the first video is to talk a little bit more serious about the need of CDN.
CDNs, content distribution networks. This is the part in video streaming services Polly finds the most amusing. Some of you might know, many of the global services that are popular worldwide uses some sort of CDN in the back. So that includes Gmail, Dropbox, even the Zoom teleconferencing system that is a bit controversial these days. The reason for that is this. You hear a little bit back, dash. Okay, so dash there is nice. The client can actually adapt. Given this much network resource, we ask for the video chunks and the version that's just behind, okay, just below the available bandwidth. So this adapts to fluctuations on the internet, which includes when the number of users increases, the remaining available bandwidth will be lower and lower. The dash there does is just to adapt to the change. The thing is that the change could become unbearable. So if the number of users increase continuously, and if a high number of them are demanding the service simultaneously, you could end up with available bandwidth that is so low, it's not even sufficient to serve the chunk with the minimum rate. And to deal with the network capacity issue is what CDN here is mainly to address for. Again, there's a critical issue on popular systems on the internet today, the scalability issue. And CDN here magically addresses some aspects of these scalability issues. Let's step back a little bit and look at option 1. So this is to contrast CDN, and this is the simple, naive solution. What about using just one server? If you recall when we were discussing DNS system, the name IP address mapping service, we were saying that originally there's only one server instead of having a distributed service, isn't it? Using one server, we have issue like this, single point of failure. That server down, the entire service down. The mega server down, the video streaming service is also down. And that one server there is also the point of congestion because everyone is asking for its service. And there'll be part of the world being happy because they are close to the server, but there will be the rest of the world will be unhappy because they are farther away from the server. And delay long is not good, and there's also a fairness issue, isn't it? How come you always get to enjoy short delay service, and how come, okay, I always have to wait? And last, this one is more distinctive in video streaming service. In DNS, the name to IP mapping are all short messages. But here, for video streaming, it's continuous, and each frame is already bigger than the name IP mapping. So we're sending these streams repeatedly, and some of the streams are probably the same. So users might be requesting popular videos, which means we are sending multiple copies of the same video over and over again. Right? Now, not a very thrifty way of using the network resource. Solution like this, definitely not scale. This is very clear. And that takes us to option 2, which is exactly what CDN is doing. That's, instead of using just one physical machine storing one copy of these content, let's use multiple machines storing multiple copies of these content. And more importantly, okay, distribute them around the internet, making sure that they are very widespread geographically. And the point of doing this is so that, hey, if there's a server here, the clients around it will be able to communicate and get the content within the local area. Therefore, the network capacity, other than this part, can be opened up for other clients interacting with other servers. Okay, so the number of duplicate video transmission can be reduced. A more efficient way, a more thrifty way of utilizing the network resource. Now, let's talk about the two models the CDNs are architecting their physical infrastructure. First one is called the interdeep. Okay, so this is actually speaking that the infrastructure, the machines themselves, okay, for storing these videos are actually deep, closer to the end customers, deep into the ISPs, to the local ISPs, so that they are close to the end customers. Akamai, one of the oldest companies, is implementing exactly this architecture. Therefore, there are so many locations around, okay, in Akamai. Pretty much for each local ISPs, Akamai probably set up a site where you see typically a rack of workstations, and they are redundantly connected to other machines in the access network, other routers in the access network, and potentially very close to the users. So Akamai there, when they deal with an ISP, they rent for the rack space, they rent sometimes for physical machines on the rack. They definitely subscribe to the connectivities provided by the local area access networks. Now, the other model is bring home model. Okay, so by bring home, these CDN architecture is to say that the physical infrastructure, the servers, okay, they're storing video contents, are actually closer to the service home, where the origin of the video sources are from. Essentially, the company generating the video. So it's actually closer to the home company. Therefore, they are actually higher up in the internet hierarchy, closer to the core instead of to the local access network. Okay, so they are actually very close to these POPs, the internet exchange points. So the idea is that such a CDN company will build up a few racks of these workstations and just connect to the POPs, where they get access to the rest of the internet. Now, because the number of locations is very limited as the number of POPs are also limited, so there are not many of these sites. And the sites tend to be bigger. Instead of calling them sites, they are called clusters. Okay, so the physical infrastructures will be formed by server clusters. Okay, few of these clusters interconnected through the POPs, the internet exchange points. So they did not go deep into the access networks. Limelight, this is a cheaper CDN service, offers bring home CDNs. Now, so you see a little bit also advantages and disadvantages of the two models. This, closer to the end customer, some big wealthy service providers might subscribe to this because potentially maintaining the infrastructure is very high cost. Now, those smaller service or smaller content providers, not quite as wealthy, then might subscribe to a bring home CDN service.
All right, so you see that there are two types of CDN architecture, bring home, enter deep. Next, I'm going to give you an illustration of how CDN works and another nickname of CDN called OTT.
Okay, and let me illustrate how the content consumer or the client, content provider, the origin server, as well as the CDN. Okay, CDN is the one distributing the content, how the three components interact. And I'm going to use Netflix as an example. All right. So client here will be retrieving a video, and origin server here, the content provider, Netflix over here. So CDNs, the content distribution network that Netflix subscribes to, will be allocating a number of physical machines worldwide, okay, and stores copies of the content. Okay, so the motion is this. Okay, a customer turned up, okay, and decided to watch Mad Men, the movie. Okay, so the user here is obviously a subscriber of Netflix, then it would send the request to Netflix. And Netflix will then send back a manifest file telling the subscriber where the copy of the video is stored. So this guy, this guy, this guy, all 7 of them will be reported to the client, to the subscriber, and subscriber then will pick one of them. Okay, so redirect it to the nearby CDN to retrieve the content. Now, what's nice about having CDN is not just the content, therefore, is closer to the client. It's also to address this issue. If the network goes bad here, okay, from the first CDN, the client there can choose a different CDN where the network congestion is lighter and go this way. And CDN working this way is also called a over-the-top service. Allow me to explain. And it's better explained illustrating it this way. So let's bring all these entities involved in a CDN service high up, like this. Okay, so you see there's a separation of the internet physical structure and the OTT service. So these CDN servers, as well as the original server, as well as the client, they form a network. It's a service network. It's a network formed by what? Hosts only. Now that's to abstract away the infrastructure here using just a channel. Okay, so you see here, high up, this is a network. And CDN, you can think of it as a service provided to the content provider such that we enable end-to-end or host-to-host communication. So it works like there's a network at the application layer. Now, maintaining such a network such that it works very efficiently distributing content is not easy. There are a lot of key design challenges. Okay, one is, hey, as we mentioned earlier in the example, right? The client will then select a nearby CDN node to retrieve the content. Okay, that is usually because the delay will be shorter, and the segment of the internet involving the communication is short as well. Therefore, less chance of other traffic interfering with this one. But how do you know a shorter delay one is certainly the one that uses the shortest segment to travel? How? And maybe you want to use a combination of short segment and short delay. So, yeah, exactly how you design selecting of the CDN node, that selection algorithm, that is something to be investigated about. Okay. Second, in the presence of congestion, well, congestion comes in very light level, sometimes very heavy level. Would viewers be really unhappy about a certain level of congestion? It might really depend. So how do you know when to switch from one CDN node to another one? Yeah, that is another challenge. Okay, so one could come up with algorithms that switch ahead of time before it goes really bad, or switch right at the point that's needed. Okay, you see that each of these strategies may carry certain advantages and disadvantages over one another. And last, wow, at the beginning, right, we said that CDN would choose a number of physical machines and maintain duplicate copies of a certain video. But which machine? And which video? Yeah. So this really has a lot to do with resource allocation and where the demands are. You want to make sure that the content is pushed closer to the demand, but you cannot be copying all the content, right, to every CDN node. So how do you conserve? Again, challenging problem. If you're curious, definitely read more into chapter 7.
All right, so that's generally how CDN works. Next video, I'm going to introduce you two example CDN services and exactly how they implement the service.
Okay, what's remaining are just 2 examples of how CDN requests are being redirected such that it reaches the physical location. So in the first example, it's more the Akamai model, which borrows from the services provided by DNS. So example goes like this. Bob requests a video from cinema.com, and this is the video ID. Okay, so browser here, browse around and decided, and Bob here hits this link. But the thing is that that video is actually stored here physically. The King CDN, a CDN company. And so it's stored on kingcdn.com's web servers, this location. But what happens here is, well, Bob's browser actually see this is the host to contact. So first thing first, ask the local DNS server for the IP address of this guy. Right? So resolve this guy. Bob's DNS server there will what? Check cache. If not a hit, go to the TLD server. TLD server will share what is netcinema.com's authoritative DNS server. And so Bob can direct the query to the authoritative DNS server for the IP addresses of netcinema.com. But what's really curious here is the authoritative DNS server of netcinema.com, instead of returning an IP address, it returns the redirected path. Okay. At this point, Bob's local DNS then resolve for this name instead. Okay. And so check the cache, check with the TLD server, and eventually reaching the King CDN's authoritative DNS server. That query goes, and finally now, King CDN authoritative DNS server will return the IP address of kingcdn.com. Okay, so IP address of this guy acquired, and step 5 sends that IP address back to Bob's web browser. From there, Bob's browser can fetch the video from the actual location of the video. Right, so this is redirecting the client to the copy through the DNS service. In example 2, the content provider here only needs to do the minimum, which is to provide the logging service. So Bob here as a subscriber just logging first. Okay, that's step 1. And quickly, Bob is redirected to the CDN. And in Netflix's case, Amazon's cloud is the CDN. So Bob here will be browsing what videos there are available, okay, and ratings and how long the videos are from the web servers Amazon has already set up. Now, once Bob has decided on watching a video, then step 3, the manifest file of that video is returned back to Bob. And Bob will begin to fetch the video from the physical machine Amazon has set up to store that particular video, and somewhat close to Bob. Last is just that the CDN server begin to dash over HTTP streaming the video. Now if we compare the two models a little bit more, we see that in the first model, the content provider has slightly better control of where the redirections should go. But in the second case, the redirection is all done by Amazon. So there's not much Netflix needs to do, or not much Netflix can do. So it's more a trade-off between control and work. Okay, so more control, more work, less control, but less work. So, well, as a content provider, you have to decide for yourself.
All right, so that was all about CDN. And we now start chapter 3. And this is the overview video.
You know what, Polly is just happy that we're starting chapter 3. The transport layer. We were at the application layer that's actually higher up. Transport layer, we're getting closer to the heart of the internet. So in the transport layer service, there are a number of important functionalities. Multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Now each of these are important, but multiplexing, demultiplexing, flow control, these two are super simple. They'll be done in like one slide or a couple slides. Now, what's going to take us quite amount of time is this: reliable data transfer, and then slightly less congestion control. All right, and both of these functions are implemented in TCP. Reliable transport, congestion control. Now then you can imagine UDP being very simple, right? It's a connectionless transport layer service versus TCP being connection oriented. So in UDP, you don't need to set up something ahead of time before we send data. But TCP, you need to have a setup process before we begin to send data packets. 3.1 is the overview section. So what I need to say here is this: transport layer services is actually providing a logical communication channel between the two processes that are running on different end systems. Right? So there's a sender side of the process, sender side of the transport layer protocol, and there's also the receiver side of the transport layer protocol. And the functions is often corresponding each other. Sender side will take messages from the application layer and break it into a number of these smaller segments. And these segments will be passed down further to the network layer. Receiver side is going to take segments from the network layer, reassemble them back to the original message, and that message gets passed up to the application layer. That's when, if this guy here sends an HTTP request, This guy over here receives the HTTP request. So the web server here can begin parsing the HTTP request and then find out what is the object being requested, right? So this is the very basic function of the transport layer protocols. Take messages from application, break it into segments, reassemble segments into message, and pass it back down to the application layer receiver. Now, that breaking of the segments, passing of the segments, and reassembling of the segments are implemented in two different flavors, TCP versus UDP. One is reliable, the other is not. Transport layer versus network layer services. So transport layer there works closely with the application layer. It works also closely with the network layer. But we have not yet talked about network layer functionalities much, so let me just break it to you. What is the main role of these network layer protocols? So what they do is to provide communication between hosts. So meaning enabling sending of messages, sending of packets, or sending of segments through the internet and reaching the other host, the destination, from source host to destination host. Okay, so that is the purpose of network layer protocols. Transport layer, however, is just to establish a logical communication between processes. Right? So between two hosts, there are often multiple processes running. So transport layer handles a pair of processes at a time. So a pair of processes, and network layer handles a pair of hosts. The granularity, okay, of the channel, the entities of the channel are very different. Okay, so transport layer here rely on underlying network layer service. So if there's a process needing to send certain segments to another process, hey, how does the sending process know which way to pass it down further? Because internet is huge and in the middle. That is the network layer protocol's job. So logical connection between the sending transport layer and the receiving transport layer, that is kind of abstract. That's why I keep saying that it's a logical communication, because the network layer is going to handle and find a clear path between the two of them. Right? Now, let me try to use an analogy to explain so that it's more clear, the distinction between a transport layer service to a network layer service. So the example is this. Anne here has 12 kids in the house, and Bill has also 12 kids in the house. Yeah, both big families. And for some reason, Anne's kids and Bill's kids are good friends to each other, right? So houses there, Anne's house and Bill's house, consider them as hosts. And each kid's generating letters sending to each other will be the processes. So 12 processes generating messages independently, okay, and trying to send them to Bill's houses and therefore reaching Bill's kids. So each letter generated by each kid is an application message. Anne and Bill will then be the transport layer service. So Anne here is the sending side of the transport layer service, taking all the envelopes and then drop it into the mailbox. So it's mixing all the envelopes into the mailbox. Bill, on the other hand, will take all the letters out of the mailbox and distribute each envelope to the destination processes, to each of the kids, right? So Bill there is demultiplexing the envelopes from the mailbox, and Anne there is multiplexing, okay, the envelopes into the mailbox. Now, the mailman, okay, taking all these envelopes from Anne's box and then go all the way to Bill's mailbox is the network layer protocol. All right, so mailman is the real person there needing to find a way and driving all the way to send all these messages. And there are two services again. TCP here does reliable transfer, but it actually does more. Packets are going to arrive in order. Packets, as they get sent, they will also be controlled. So sometimes you can send faster, but sometimes slower. And usually it's when there is congestion that you send slower. If there's not congestion, TCP sender side will be sending more aggressively. There's also flow control, connection setup. Flow control is such that we do not overwhelm the receiver side buffer. Okay. Connection setup is, if you heard, TCP is a connection-oriented services as well. In order to provide these functionality, reliable transfer, in order delivery, congestion control, and flow control, well, the sender and the receiver side of a TCP connection needs to, communicate a little bit more before setting up a connection. So that takes some time. So there's a connection setup process as well. UDP, on the other hand, is the complete opposite. It's not reliable. It does not guarantee order delivery. So UDP is essentially nothing versus TCP does a lot. So essentially at the transport layer, you have the two extreme of the services. So it's on top of the network layer, which is called the IP protocol, and it's best ever, meaning do nothing. All right, so no field extension of IP. And so UDP there is very simplistic. Take messages from application, break them into segments, pass it out. Receiver there, grab the segments from network layer, and then try to reassemble them back to the original message and pass it up to the application layer. Now, if there's any segment lost in the middle, that message gets passed up to the receiver side of the application layer protocol. It's not going to make too much sense, right? Oh, and TCP, UDP, one does reliable transfer congestion control, the other does nothing. None of them provide this delay guarantee, bandwidth guarantee, and none of them provide security guarantee. Okay, and you heard it earlier, the security is provided by this alternative service, but this alternative service is in fact implemented in the what? Application layer.
All right, so that was the overview. Okay, you see a little bit more transport layer. Above that, there's application layer. And below that, there is the network layer. And in the transport layer, just two services, TCP and UDP. Now let's talk a little bit more about the multiplexing and demultiplexing functionality. This functionality is implemented both in TCP and UDP. It's the very elementary and important functionality.
3.6 multiplexing and demultiplexing. Well, if you still recall the end bill example, end kids sending to bill kids example. End is the multiplexer, and bill there is the demultiplexer. Right? So if we focus on this example below, so this guy in the middle is a big server machine. There are multiple processes running. You see here, P1 is sending a message out. P2 is also sending a message out. Yeah, the transport layer at the server is doing this, multiplexing. So this host here, from P1 and P2's point of view, generating this message, okay, is the sender. Okay, so sender. So it handles data from multiple sockets or data from multiple processes. Add the transport layer header, so add a little bit more information on top of these packets. Okay. And so therefore, later they can be used for the demoxing purpose. So when messages go out and reaching P3 and P4, and P3, P4 in return generates something back as it arrives back to the server at the transport layer. Yeah, transport layer of the server is going to be working as a multiplexer at the receiving side. And what it does is to look into the header, okay, in these packets, and then decide whether it should be this socket, the message being forwarded to, or this other socket, the message being forwarded to. Right? So very simplistic, but very important functionality.
All right. And that takes us to quiz 16. So you heard about multiplexing and demultiplexing on the internet, but in a snail mail system, okay, we also do multiplexing and demultiplexing, but we are not realizing that those actions are called multiplexing and demultiplexing. So what I'm showing here on quiz 16 are two pictures. On the left, picture A, you see those are the big boxes that we could actually walk and insert the envelopes that we have, insert the mails we have wanting to send to other people. Okay. The picture on the right, B, that is a mail person, okay, and she's obviously trying to sort the mails and find out which individual boxes these mails should go into. All right. So Q1 is asking, okay, which device is the multiplexer and which is the demultiplexer? Okay, so there, Paul, you actually said a little bit too fast in the video. The sender there is the multiplexer. The receiver is the demultiplexer. Okay. And Q2, what's on the envelope, okay, that allows the demultiplexer to demultiplex, to sort the mail out. Okay. And let's go to the Slack space. Okay, so there's a channel called W7-quiz16 being created. Okay, if you add the channel, I think if you go to the top, okay, channel, you see that there's a plus sign here. You can click and then choose to add W7 quiz 16. Then you are in the channel. From there, you see exactly the quiz problem and type up what you think. Is it A being the multiplexer, B being the multiplexer, or the other way around? Which one is the demultiplexer? And Q2, what's in the envelope allowing the demultiplexer, okay, to sort the mail out so that they know which individual boxes to send the mail to. Oh, okay, I see. Team 5 cannot wait. Ooh, all right. Let's allow a little bit of time here.
Hello!
Oops. YouTube commercial. Sorry about that. Let's mute that. All right, I think it's quite obvious, right? You guys are all typing things up. So the delay typing things up is probably longer than thinking. Yeah. Good, so it's very obvious. As I said it again, sender is the multiplexer. Okay, so you have multiple processes, you have multiple users walking to the mailbox and drop the mail. So those mailboxes are the multiplexer. Okay, very good. And on the other hand, the mailman then will have to sort all the mails out, right? And drop them into maybe the box for apartment number 101, apartment number 202. Okay, so the mailbox or the mailman being the demultiplexer. And what's on the envelope that's separating the mails so that you know exactly which destination mailbox to throw in? Yeah, the name, right? Or the apartment unit number. Okay, so in Taipei, we live in apartment buildings. So usually when the mailman arriving in a building, the mailman is mainly looking into the unit number, okay, to separate the mails. But at a level higher, for example, when a mailman arriving on a particular street, then they will probably share the city, the zip code, the street name, but not the address number, right? So you see that the address is the physical address that we're sending physical mails are hierarchical, much like what we are doing there on the internet. So we'll talk about IP address. There's a certain hierarchy there as well, but that's in the network layer. Good. So you guys all got the idea. So we are not quite yet done with multiplexing and demultiplexing. Okay. So let's talk a little bit more into the detail of doing multiplexing and demultiplexing. The multiplexing, you can see that it's very straightforward. We just mix things. Okay, one doesn't need to be intelligent and checking anything. But demultiplexing is actually the component that's a little bit complex. The demultiplexer need to look into some information in order to judge where to Dmox the mail to. So that's looking to how the internet, a transport layer connection, Dmox packets.
Now back to the lecture. If you think about it a bit more, multiplexing and demultiplexing, which one is more trivial and which one is less? Yeah, multiplexing, just collect the letters and shuffle it into the mailbox, right? No brainer. But mailman will have to, Bill will have to look at the envelope and see who the envelope is addressed to. So demultiplexing there is less trivial. Similarly, on the internet, the transport layer services receiver also needs additional information, just like the names on the envelope, to do demultiplexing. So the information the receiver side of the transport layer service relies on are these. Okay, the source, destination IP addresses, and the source and destination port number. Right? Now, let me explain. The host that's receiving a packet is going to see this, the IP datagram at the network level. Okay, not quite yet at the transport layer. We are now at the network layer, the receiver's network layer. So what we're seeing there is a packet that we call the IP datagram. So let's call this the datagram. Okay. So now a datagram is composed of the header part and the payload, the data part. Okay, so header here and data here. Inside the header, there are these fields, the source and the destination IP addresses. Okay, so these information are kept there. So it's a network layer information. And each datagram also carries a transport layer segment, which is this, the data part of the IP datagram. So this here is exactly what's depicted on the side here. It's a segment. Similar to datagram, a segment is also composed of two parts, the headers and the data part. So the segment's header contains source and the destination port number as well. Right? So source, destination IP together with source, destination port number, they are the information to allow the transport layer services, the receiver side, to do demultiplexing. Okay.
All right, so that was how it works in general. The special information is stored in the packet header. Okay, so the poly is rushing a little bit to save us a couple seconds. Now let's look into connectionless multiplexing, demultiplexing first. It's the easier form.
And the first form of demultiplexing is called connectionless demultiplexing. And this is also the kind of demultiplexing being carried out by a UDP connection. All right. So in this type of demultiplexing, we rely only on the destination IP address and destination port number to decide which socket to pass a packet towards. So it's only a two-element tuple. So when a host receives an UDP segment, it checks the destination port number in the segment and then direct the segment to the socket carrying that port number. And that's pretty much it. Now, of course, the IP address is important because the host at the network layer would be able to decide, whether this particular host is the destination of this packet, therefore keeping the packet and pass it up to the transport layer. And the transport layer could handle this. Yeah, receiving a UDP segment, check the port number, and so on and so forth. All right. So datagrams with different source IP address and different source port numbers, as long as they come to the same IP address, same destination port number, they will be going through the same socket. Okay. So demultiplexing for UDP is slightly simpler. All we care about is the destination address and port number. So here's an example of connectionless Dmox. So port 9157 is where P3 is sitting on, so that's one of the clients. Port 5775 is process P4 that is sitting on, so that's another client. Server in the middle, open up port number 642A, and P1 there is the server processing. It's waiting for requests to come in. So we see here a service request message being generated from P3 and intended for P1. You will see source port number being 9157 and the destination port number being the server's port number 642A. And the return messages, so replies from the server will then be carrying the source port number being the server's port number and destination port number being the sender's port number, the original request sender's port number, 9157, the client's port number. So you see also a little bit that how P1 can generate the reply. The port numbers are essentially the reverse, okay, of the requests. Now, if there's another request coming from P4, what is going to be the source port number? 5775. And destination? The server's port number. And it's probably not hard. The returning messages back to P4, source being 642A, essentially the reverse of these two port numbers.
All right, so that was straightforward. That is exactly what the UDP connection is doing, mixing packets and demixing the packets. The last one is connection-oriented Dmox and Mox.
The slightly more complicated one is the connection-oriented Dmox. That is also the TCP's demultiplexer. So whether a packet or a segment should go to a particular socket depends on O4 information. All right, so receiver uses O4 values to direct the segment to the socket. Now, a server process running there on the host could be maintaining multiple sockets, okay, for each pair of communication per client. So for example, a web server, the web processes there could have multiple sockets open for each of the connecting client. And if this is older form of HTTP the web server is running, it could be one socket per object request. Now let me use an example to illustrate and explain. So we have a scenario where we have three segments being sent from clients over here, A and C, to the server in the middle, B. So all three segments destined to B, and they're supposed to be demuxing two different sockets. Now, P4 sockets will be using a 4-tuple to decide. And what will be the 4-tuple? Well, source IP address, A, destination IP address, B, and what? Source port number and the destination port number. So these four values is going to be associated with this socket. So when there's a segment arriving at the transport layer, matching the 4-tuple, therefore going to the socket. Similarly, for each of the sockets here and there, the 4-tuples will be stored, and the transport layer looking at the packet header, when there's a match, pass it up to socket to the processes. So that's the idea behind connection-oriented Dmox. And the reason it's called a connection-oriented Dmox is because it's not only looking at the destination, it cares also who the sources is. So it's almost like there's a one connection between the source and destination already, okay, the socket. Now, this connection-oriented Dmox socket is a little bit weird. And this actually happens quite often these days when we're doing this threaded server. Okay, so in your PA4, you are implementing a server, all right. What happened there is that you are starting a listening socket, isn't it? Listening socket is a little bit special because no matter where the client is, whatever the source IP is, request coming in, it's going to be passed to that server socket, that listening socket, all right, even though the 4-tuple does not quite match, especially the source IP address and the port number. Okay. This type of connection-oriented Dmox, it is TCP, all right, but it only looks at the destination port number and the destination IP address. Therefore, the message is coming out this way, source being A, source port number 9157. This one here, source being C, port number again different. But then they will all be accepted by the listening socket here.
All right, so let me clarify just a little bit more. When the other clients send requests to the server there, it's going to the same port, same listening port. They will be all accepted, but subsequently, individual sockets will be created, okay, for the subsequent communication between the client to the different threads of the server. All right. All right, so we don't have time really to get into UDP. So that's why I try to rush to get a few seconds ahead because the next video is about 4 minutes and 30 seconds. but turned out that we will have trouble really play the whole video through. So I'm just going to hold that and introduce UDP more formally tomorrow morning. All right. So that's going to be all for today. With that said, feel free to go. Oh, wait. There's a question on the chat room. So let's see. Wei Yuan is asking, Polly, I wonder if you will give test file for PA4, much like PA3. You know what? You use the exact test.txt that you use for PA3 for PA4. Okay, because the way you test PA4 is to run your own PA3. Okay, and to run PA3, you use the PA3 test.txt. All right, very good question. Now you have a good handle of where to start working for PA4. Let's see, there seems to be another question. Okay. All right. So good. So hey, guys, have fun at the EE night. Okay, I know that it's one of the big things for the undergrad students. Okay, so goodbye. I see you tomorrow morning. Okay. All right, so Polly is gonna stay on for a little longer in case you have questions, and I understand that it might take some time to type them up. Okay. Bye, go. I know some of you are actually preparing. You need to dance, or you need to sing, or you need to act, or you need to, move stuff around or decorate and put things on the stage. Yeah. So go on and do the rehearsal. Okay, bye. Have fun. Ouch. Okay. So Wei Yuan, how about borrowing other teams' PA3 test.txt? Okay. So ask maybe team 2. Oh no, Zewei also deleted PA3 test. Ouch. Okay, so I can probably upload it somewhere, and so I can post the link to download the file. Oh, okay, very good. Okay, good. Okay. So, hey, Wei Yuan, copy the file from Zewei, I think team 2. Oh, you're welcome, Angel. Okay, I hope the pace is working for you. So we kind of rushed a little bit. All right, so I see you tomorrow, maybe. Okay. All right. Oh, okay. Lots of love from Wei Yuan here. All right, so time up. Polly is going to end the stream, and let's see each other tomorrow.